Okay, let's analyze now what happens when we have an object rolling down an incline without slipping. So once again, this is without slipping. So when an object is rolling down an incline without slipping here, we're going to do just what we've always done, where we use Newton's laws in two different ways to analyze the translational motion of the body, or of the center of mass of the object as it moves down, and analyze the forces acting on the edges that could be supplying a torque, or at least acting away from the axis of rotation. All right. So let's say the axis of rotation is here, and right away we know that the thing is going to accelerate down the ramp. If it is accelerating without slipping, once again we know that this has got to be true, that the acceleration and the rotational or angular acceleration have got to kind of correspond to each other. So I know that it's got to be rotating around this way, that the alpha here has got to be clockwise if the acceleration is down and to the right, like that. Okay, just like always, whenever we analyze objects moving up or down inclined planes, we want to rotate our reference frame. So I'm going to rotate my reference frame here, and I'm going to draw now a free body diagram for this object. The normal force goes up, and you really have two options for how to draw the normal force. I very vaguely alluded to this earlier. You can draw the normal force from down here, because that really is where the point of contact is for the normal force. But you are also perfectly fine drawing it from the center of mass as well. I'm going to draw my normal force from the center of mass, which is also the axis of rotation. So there's my normal force. I've swung my reference frame, so before gravity was pointing straight down from the center of mass, I just rotated my reference frame by rotating the whole thing this way. So gravity, you know, gets swung out like this, and you know that I can break gravity down into components now. This angle of the ramp shows up right here. Let me use a different color. All right, so there's the angle theta. And of course, as we've done a million times, we know that this ends up being mg sine theta. And this, of course, ends up being mg cosine theta. All right, and what force am I missing? There's a frictional force, isn't there? And the frictional force, I need to draw it from its point of contact right here. And that frictional force is going up the ramp, and it's a static frictional force because once again I'm rolling without slipping. Okay? All right, and let's say that this thing has a radius of r. How do I know that the force of static friction has to point that way? That's what we would expect, because the thing is translating down the ramp, so there must be a frictional component up the ramp. Well, that is the only force that's supplying a torque here. I want you to remember that torque is the cross product of r and f, where r is a position vector drawn from the axis of rotation to the point of application. Well, here's the axis of rotation. Every other force here has a point of application right there at the axis of rotation. Gravity does. And then the normal force, even if we did draw it as coming from down here, it would be perfectly parallel with that vector drawn from the axis of rotation to the point of application. And you know that cross products are worried about how much perpendicular the two vectors are, the perpendicular components, the sine of the angle between them. So no other force is supplying a torque to cause the thing to rotate, to roll, just this one. So the first thing I can do is, why don't we do the translational one first, sigma f equals ma, and we know that mg cosine theta has to equal the normal force, And we're not worried about the force of gravity because we've broken it down into its components. So I know that the thing is accelerating this way, that's down the ramp. So mg sine theta would be my accelerated force minus the force of static friction, where we haven't mentioned this in a while, but I know that the force of static friction is equal to the coefficient of static friction times the normal force. And here the normal force is equal to mg cosine theta. Now, whoops, forgot my S. Now, remember that the coefficient of static friction has like a maximum that it can reach. I don't know if I've reached that maximum. Does that make sense? So really what I should say here, because I don't know if the force of static friction has reached the maximum that it can, I know that the force of static friction is less than or equal to mu s, where mu s is like the max, mg cosine theta. So really this should be an inequality. I haven't emphasized this enough, and I do want to pause to emphasize it now. This should be an inequality here because I don't know necessarily if I'm at the maximum value. Does that make sense? Remember, as I mentioned earlier, with friction, the force of friction, reaches some maximum static, and then the two surfaces do start to slide over each other. That's where we get kinetic friction. So the force of static friction really depends on the context. We may not necessarily be at that maximum value, hence the inequality. So we can ask all sorts of interesting questions. I can actually figure out what the maximum angle is such that this thing does not slip and skid. What's true if this thing starts to slip and skid? I no longer have static friction, I have kinetic friction. In other words, I've overcome the maximum threshold for maximum static friction. So that's one interesting thing that we could think about. For now, why don't we assume that we are just at that maximum value, and then we can just say that this is indeed an equality here. This is equal. That's one thing we could do. So I'm just going to let that be my force of static friction. So there's Newton's second law translationally, as we've done many times before. Newton's second law rotationally, sum of the torques equals I alpha. So again, the only torque that I have here is the static frictional force, coefficient of static friction, mg cosine theta. And remember that torque is r cross f, where the r is the vector, the position vector from the axis of rotation to the point of application of the force. And that's just going to be, it's going to have a length of r, the radius of my wheel or disc or whatever, and they're going to be, those two vectors will be perpendicular to each other, so I don't need to worry about the sign of the angle between them. So I just need to put an r in here, just like that. I don't have any other torque that I need to subtract away or anything, so that's going to equal I times alpha. I can rearrange alpha just like we've done many times before, A over r. Just like that. Okay, so from these two equations, we can combine them to solve for many interesting things. Maybe we do want to know, like, what is the value of this mu s need to be for all of this to be true, for the thing to truly roll without slipping. In other words, what is the minimum value of the coefficient of static friction between this object and the incline so that it will roll down without slipping? So what I want to do now is try to solve for mu s. Okay, I know that if mu s is like too large, then all this will fall apart. I know that I need my frictional force to be smaller than some value. So I want to know what is the minimum mu s that I need in order for this thing to roll without slipping. So that's one question I could ask. In other words, I just need to solve for mu s. So Let's see, what do these two equations have in common that I can, maybe put them in terms of each other? Well, it looks like I could rearrange for acceleration and plug that in here, couldn't I? So let me do that. Divide both sides by m to get acceleration and plug it in for this acceleration here. So I divide the top equation out by m to get my acceleration, g sine theta minus mu s g cosine theta, to get my acceleration there. That's this equation, divide it out. And then I can plug that in for the acceleration right here. Just like that. I'm just doing some algebra. Okay, so let me explain what I've done so far. So all I am trying to do is get an expression for the coefficient of static friction from these two equations. So I just divided m out to get a equals blah, plug that in here. Now I have one expression that looks just like this. And I'm just trying to rearrange to solve for mu s. So I start to try to collect my variables, and ultimately I get here. And then I want to talk about I. I haven't fleshed that out yet. Remember, I is rotational inertia. And remember, I is always like some value of mr squared. Like for a disk, it's 1/2 mr squared. For a hoop, it's mr squared, etc., etc. It's always something mr squared. So all I've done is just replaced I with k mr squared, where k is this constant that ends up coming out here depending on what the shape is. I haven't said exactly what the shape is. It could be a solid sphere, a hollow sphere, it could be a cylinder, a hoop, whatever. Okay, so that's all I've done here. I've done that because I recognize I had an mr squared on the top right here, and I know that I has mr squared in it. So that gets me mu s times 1/k, where k is just the fraction. mg, nope, the m canceled out, didn't it? G cosine theta plus g cosine theta equals g sine of theta. And I recognize that I have a g in every single term, so I can just go ahead and cancel out that g. I could have done that a long time ago. So cosine of theta times 1/k plus 1. All I've done is I took the g out everywhere because it's in every single term. And then I factored out a cosine theta. And then I can just divide by this. And I get mu s has got to be, equal to tan theta, because sine over cosine is tangent, times 1/, this wacky thing, 1/k plus 1. Where again, that k value is equal to whatever ends up in front of the mr squared in the I rotational inertia value. So this term, now remember I've put an equal sign here, but remember that the force of friction always needs to be less than or equal to this value that we've plugged in here. And so really what I found is the minimum value of the coefficient of static friction in order for this thing to roll without slipping. Right here. So if the coefficient of static friction is what I'm interested in solving for, I rearrange and I solve for it. I could have also rearranged to solve for the angle theta. What is the maximum angle that this thing can have to roll without slipping? I could have solved for that. I could figure out things for what the different coefficient k has to be, where again, I is always equal to some k times mr squared, where that k is like 2/5, 1/2, etc., etc. So there's lots of questions I could ask. It's just an algebra game. I'll let you play the algebra game kind of on your own. If you have questions, let me know. But deriving equations like this is what the College Board is interested in seeing. What I'm interested in right now is that you understand the concepts of an object rolling without slipping down an incline. First of all, we have to think through what's happening translationally. We have to think through what's happening rotationally. And there's really only one torque that's being supplied by the force of friction there. And then we use this identity, these things which are true only when the thing is rolling without slipping, just like that. Part of the very first thing I did was recognize that because this is true, it's rolling without slipping, and because I know that the translational acceleration is down the ramp, that has got to correspond to what is happening rotationally. It must be rotating clockwise like that. All right. Went through and I drew my free body diagram, and that allowed me to think through translational motion, extended rotational motion. Of course, for my translational motion, I could have treated the object like a point particle. I would have gotten the exact same result. We've done this many times, right? And then I started solving for what I wanted to solve for. In this particular case, I was asking, what has to be true about the coefficient of static friction between these two surfaces? I could have very easily asked about the angle. I could have asked about the shape of the object. What does this I value need to be given other parameters? Okay? So what if I wanted to solve for the acceleration now? And get acceleration in terms of other things that might be interesting. What I can do is recognize that these two equations, which are my two guiding equations right now, they both have this term right here. This one has an r in it, so what I can do is divide the r away. Let me do that real quick. I'll just rearrange this, divide both sides by r, and I'll get an r squared down here, won't I? So I can do that. And I can plug IAR squared in right up here. And we get mg sine theta minus IA over r squared equals MA. Try to collect my terms. Mg sine theta equals MA plus IA over r squared, factor out an a, mg sine theta equals a times m plus I over r squared, divide and get an expression for a. A equals mg sine theta over m plus I over r squared. And of course, what we could do is recognize that I has an m and an r squared in it, and we'd end up with something interesting there as well. I'm just trying to show you guys that once we have set up these two equations, our translational Newton's law, our rotational Newton's law, then we're really good to go to solve for whatever they could ask us to solve for. The key parts of this that you remember, that these statements are true and that the force of friction is static force of friction only when the thing is not slipping. Now there's one more thing I mentioned earlier about objects that are not slipping as they roll, and that is that kinetic energy is conserved. So I want to show you now something we've not talked about, a new concept, which is rotational kinetic energy. Pretty simple and straightforward. In fact, I think I did mention this just briefly at the very beginning of me talking to you about rotational inertia. But kinetic energy for rotating objects is equal to 1/2 I omega squared. Remember that for translational motion, it's 1/2 mv squared. So this should look really familiar to you. It's the exact same expression, just translated for rotational stuff. M is inertia, I is rotational inertia, v is velocity, omega is rotational or angular velocity, right? So what we could do is use this idea to talk through some things that we have been looking at as well. Okay, so we can take an energetic approach to all of this. So here I have an object, maybe it's a ball or a wheel or a disc or something, that is up on an incline, it's inclined some angle, and it has a height h. Now, we always want to be careful to define where our zero line is for gravitational potential energy. Hopefully you remember that. So this is kind of nitpicky, but I do want to point out that you do have to think about this in some cases. Gravitational potential energy, we can say that we're really concerned about where the center of mass is located of this object. This object, from the ground level down here, the center of mass is really not at a height h. Its bottom part is at a height h, but its center of mass would be elevated h plus r, whatever the radius is. So just to make things simple, I know that when this thing rolls all the way down and it has, it no longer has any gravitational potential energy, I know that its center of mass will be above the ground by a radius r. So all I've done is I've just shifted my zero line up that amount. The difference here is still a height h, so it really truly does not matter. It won't affect my calculations, but it is something that is going to be good for us to think about. Where are we defining the height from? I like to do it from the center of mass of the object. So energetically speaking, remember, when is an energy approach useful? For analyzing initial and final states. So I know that initially my object has gravitational potential equal to mgh, and at the very end, at this exact instant, I know that it's going to have both of these things. It's going to have rotational kinetic energy and translational kinetic energy. So 1/2 I omega squared plus 1/2 mv squared. Now, right away, thinking about the fact that this thing is going to be rolling and speeding up, it's rolling all the way down. We can see that by including this rotational energy term, all the object had access to was gravitational potential energy at the beginning. And so if we ignored rotational kinetic energy, we would just write this. And we would get a velocity there. If we solved for the velocity down here at the bottom, we get a velocity bigger than we're going to get in this analysis. In other words, taking into consideration the fact that it's rotating, that it's rolling, that it's going to have some rotational motion and therefore some rotational kinetic energy, means that there's less energy available for its translational velocity. Translationally speaking, it's going to be going more slowly. Okay? So just keep that in mind. Oh, shoot. Okay. And remember what is true for something that is rolling without slipping. The velocity of its center of mass is related to the angular velocity, isn't it? Omega r. Rearrange this and say that omega is velocity of the center of mass divided by r. I can plug that in right here. So mgh is going to equal 1/2 I omega squared v squared over r squared plus 1/2 m v squared. And now if I know what the I value is, then this equation will become much simpler. And remember what every I has in it. It is something 1/2, 2/5, something mr squared, isn't it? I think in the past I've said that's like a k value. So I'm going to have an m show up, and I'm going to have an r squared get cancel out. And you can see then that based on the I value, I'm going to be able to think through how much of the energy ends up being trapped in rotational motion and how much ends up being free for the true translational kinetic energy. Let's plug this in with K and see what we get. So now we could play around with this based on the shape of the object. For example, a hoop has an I value of just mr squared, doesn't it? So in other words, the K right here is equal to 1. And so you can see if that's the case, my gravitational potential I have at the beginning is going to end up getting split 50-50, won't it? Because these velocities are the same, it's going to get split 50-50 between rotational and translational kinetic energies. So that's true for a hoop. Let's see, what if it is a disk? For a disk, we know that the I value is 1/2 mr squared, so the K, as I'm calling it, is equal to 1/2. So I would get 1/4 mv squared plus 1/2 mv squared. The rotational energy is now less than the kinetic energy. I'm going to get a bigger final velocity. Rearrange this, and we're going to get that v is equal to 4gh over 3, the square root of that, which very clearly equals 2 times the square root of gh over 3. So that's going to be the final velocity, translational velocity of this disk. Now, it may be illustrative to actually work out and solve for what the final velocity of the hoop must be. So again, for a hoop, the K value, where K is what I'm calling the fraction that ends up in front of the mr squared of the rotational inertia term, for a hoop is just 1. So I can plug that in here. mgh is going to equal 1/2 mv squared plus 1/2 mv squared, where K is 1. And my m's all cancel out. 1/2 v squared plus 1/2 v squared is very clearly v squared, so I get gh equals v squared. Rearrange that, v equals the square root of gh. So you can see that for the disk, because it has a smaller rotational inertia, it is, so to speak, stealing less energy away as rotational kinetic energy, leaving more energy left over for translational kinetic energy. Compare the velocities. This is clearly bigger than this. I'm multiplying by 2. I am dividing by the square root of 3, but the square root of 3 is smaller than 2, so I still end up multiplying this velocity compared to this one. Okay, so the smaller your I value, means less energy gets converted as rotational kinetic. Assuming that we are looking at objects that have the same mass and the same radius. So now we can ask this question. Which will reach the bottom of a ramp with greater speed, with greater translational speed? Is it going to be a solid sphere? Is it going to be a hoop, also known as a hollow cylinder, same thing? Or is it going to be a solid cylinder or a disc? What's up, bud?
This is to learn more, go to unlimitedsquirrels.com.
Oh, we should go there.
Yeah, but I don't know how. You know how.
Well, it's a website I can type into the internet.
Oh.
We can do it later. Well, guys, remember that we've already said that as long as energy is conserved, and remember, energy is always conserved for rolling without slipping. So gravitational potential energy is going to become rotational kinetic energy, 1/2 I omega squared, plus translational kinetic energy, 1/2 mv squared. And we know that V equals omega R, or omega equals V over R. So we can sub that in right here. mgh equals 1/2 I V squared over R squared plus 1/2 mv squared. And again, we know that I is always something times mr squared. So all we need to do is compare the I values. The bigger this I value, the more energy has got to go to rotate the thing to rotational kinetic energy. So all we need to do is compare the I values of these things. I can tell you, I might recommend memorizing these. It may be worth your time. Don't worry if you can't, though. The I value for a solid sphere is 2/5 mr squared. For a hoop or hollow cylinder, it's mr squared. And for a solid cylinder or disk, it is 1/2 mr squared. So you can see that the hoop or the hollow cylinder is going to translate most of its energy to rotational energy. The solid cylinder or disk is going to be next, and then the solid sphere, 2/5 mr squared, that's the lowest I value out of all of these. 2/5 is less than 1/2. So we know that the solid sphere is going to translate less of its energy into rotational kinetic energy. You can actually work this out to figure out what the velocities are, to actually solve for the velocities. If you plug 2/5 mr squared, 1/2 mr squared in for I. But just thinking about it conceptually, I know that the I value for a sphere is less. That means it takes less energy. It takes less of a force. It is easier to cause the sphere to rotate. So less of its energy is going to go towards the rotational kinetic energy, leaving more energy for translational, leaving there a higher velocity. All right, so the answer is the solid sphere. The solid sphere is going to reach the bottom of the ramp with a greater translational speed. In fact, it should reach the bottom of the ramp first if the acceleration is constant the whole way, because the whole way it's going to have a greater velocity. So the solid sphere is the correct answer. I want you to think about the fact that we could also answer this using a forces approach. So once again, here's my object. I know the object has some I value. It's going to be accelerating down, and it's going to be accelerating around with a rotational acceleration like that. So do my free body diagram using Newton's second law. Rotated reference frame, here's mg. mg sine theta is the force accelerating it down the ramp. mg cosine theta is the force perpendicular to the ramp that counteracts the normal force. And then, of course, here's the force of friction. So I know that the force of friction is the normal force, which is equal to this times the coefficient. And that is my resistive force, so it's being subtracted away from my accelerated force of mg sine theta. And I know that has to equal ma, just like that. And then I can do my extended free body diagram, where I'm really only worried about the frictional force because it's really the only thing causing a torque to give me that angular acceleration. So I can say that the force of friction, which is coefficient of static times mg cosine theta, times r times the radius here, that's going to be the torque, equals I alpha, just like that. It is not slipping, so just like we've always done, A equals R alpha, or alpha equals A over R. Plug that in here. This is just the derivation that we did before. I can divide both sides by R. This term shows up right up here. So now I can combine my two equations and get mg sine theta minus this, just like that. And now rearrange and start solving for acceleration. Just like that. So you can clearly see that the bigger the I value, means smaller acceleration. And smaller acceleration means it's going to take longer to go down the ramp, and it's going to have a smaller velocity at the end of the ramp. Or at the bottom of the ramp. So we can answer this question using a dynamics approach. The bigger the rotational inertia, the smaller the acceleration is going to be. And in fact, we don't even have to do all of this. We can just go straight to this. The fact that these are true for rolling without slipping, recognize that acceleration is going to be proportional to rotational acceleration, and understand that Newton's second law for rotation basically says that for a given torque, the bigger the inertia, the smaller the rotational acceleration is going to be. So very clearly, bigger inertia, bigger rotational inertia, bigger I value means smaller rotational acceleration. Smaller rotational acceleration means less acceleration overall, which is exactly what this equation ends up saying. The moral of the story that we want to learn and think about is that when things are rolling, they have a new type of kinetic energy that we have to think about. It's called rotational kinetic energy. Rotational kinetic energy, it is just mapped exactly onto translational kinetic energy, 1/2 mv squared, 1/2 rotational inertia, rotational angular velocity squared. And now we're saying that whenever something starts at the top of an incline with gravitational potential energy, once again, as long as it's rolling without slipping, energy is perfectly conserved, okay? So the gravitational energy I had at the beginning is going to go to not only regular, plain old translational kinetic energy that we know of and that we've worked out many times in the past, but also some of it is going to get sapped away into rotational kinetic energy. All right? Okay.